All right. So, all right. So we're going to kind of talk about natural language processing. So I know, like, Matthew, you weren't here last time, but we actually went from section 43, which is like intro to natural language processing. We talked about basically how to process, text values, so like stemming, lemmatization, all that stuff. And section 43 also includes a little bit of feature extraction, which we didn't really get into. But we'll talk about that today. And then we'll go into section 49, which is going to be talking about, like, okay, feature extraction was 43. And then one of the things that it talks about in 49 is a big focus on word embedding. So we'll talk about like what word embeddings are, what you can do with them. And then we'll talk about the modeling aspect too. So I'm going to come through a few things today. To be honest, I probably won't dwell too much time on the modeling aspect of 49, just because there is a whole lot to it, but actually implementing it is not too difficult. And this is where, if you follow the labs along in section 49, you probably get a pretty good feel for like actually implementing it and everything. But of course, we'll go through all that stuff. Okay, so let me go ahead and close up. No, not close up. I want to share my video or share my screen. Okay, so here we go. All right, so feature extraction. You guys can all see that feature extraction notebook? Okay, cool. And just kind of very, very quick, intro to NLP, right? We talked about this, what NLP is useful for, text processing. We talked about basically all these different steps, especially the cleaning, normalization, capitalization, all these different parts, or normalization, tokenization, all those parts, basically getting our text ready. And then this assumes, like, okay, we have our text ready, how do we extract features? And this is where feature extraction is going to be really important, because in practice, and this is not just NLP, but in general for machine learning, is that the most kind of like bang for your buck usually isn't making a more complicated model. It's actually taking more time to get the right features out, whether that's, combining new features in there, getting new data, putting it in there. That tends to be a lot more fruitful than just giving like a more complicated model. So for NLP especially, because the data can be very complicated, picking out features can actually be very fruitful. Okay. And just for the record, because I know like Matthew wasn't here before, and then I know if Raphael's cohort is going to watch the recordings, you guys can find these resources under that repo under NLP. That's where I'll have everything in there. Okay. So let's go into feature extraction. And we didn't talk, like, just give me a thumbs up, guys. We haven't done this part, right, last time. Feature dependent on tasks doesn't look familiar. Okay, good. I just wanted to make sure. All right, so the main thing that you have to know is that for features is that it depends on the task, right? And so note that I kind of talked about, you can think of it as the full document level, or you can think of it as like, the sentence level. So it depends on like what you're going to grab, right? And there's a bunch of different ways you can do feature extraction. One thing I didn't even mention here is something called bigrams, which the curriculum actually mentions about is another set of features. It's just another way we can kind of like basically take a new feature out of it. And I'll mention it briefly when we get to it. But the main thing is that you should know what your task is. So don't just blindly just apply features, and also know kind of what resources you have and what kind of it takes to do these different resources. For example, I kind of more or less label this bags of words, TF-IDF, and word embeddings, kind of in the sense of like complexity, is that bag of words is relatively, straightforward, but doesn't have as much complexity. TF-IDF does a little bit of extra stuff. And then word embeddings in a lot of ways is like probably the most complex one that we're going to talk about today. And just know that that means that word embeddings can actually contain a whole lot of information without you even doing any modeling. But to build up those word embeddings can actually take a lot of effort. So you have to know what thing makes the most sense for your problem. Okay. So let's kind of move on to like bag of words, right? This is kind of our first one. So a bag of words, when we talk about this in NLP, we're talking about like an unordered set, or like a bag of tokens representing a document. So remember, tokens, you can kind of think of it as words, but just know that they're not technically words. Now, note that when I say like an unordered set of tokens, what I'm really saying is that I'm taking a bunch of just like the tokens and saying, oh, this occurred in, let's say, the sentence or the tweet or whatever the element, the document is in your corpus. So I'm just saying, oh, was the word, dog used? Oh yeah, dog was used. Oh yeah, it doesn't really care about where it occurred. Okay, so you can see it's relatively simple. So kind of a quick knowledge check, right? We can just keep the tokens as separate sets. Like just say, oh, like have we talked about, are you guys familiar with Python sets? in like Python. So you can actually build up a set in Python and just say, okay, like, you know, just whatever's in it. There's no order. It's not like a list. There's no repeats and stuff. Why might that be a bad idea? Why might you not want just a set of just saying, oh, did that occur? Yes or no, not how many times. Anyone can think of like a reason why that might be a bad thing or might not be the most efficient thing.
You're gonna want to know what words are used more often, depending on your goals.
Mm-hmm. Yeah, I think that makes sense, right? Like, I think you guys intuitively know this is like, if a word gets used over and over and over again, it's probably something important about that corpus, that text, right? Like, I'm gonna use like the word like, I don't know, I feel like God or something like that, right? So God is gonna occur a lot of times, probably like, you know, in like the Christian Bible over something like Moby Dick, right? And that kind of gives a little more context of, you know, like of what that text is like, right? And so you can kind of think probably like, I'm not as familiar with Moby Dick, you know, like, but I'm assuming God probably like, I'm like, oh my God, or like, you know, something like, you know, like it can probably be used, right? It's a pretty big text, right? But using the word God, like just one time, like versus like however many times it happens, you know, like in the New Testament or something like that, it's going to describe something different about those texts. So it's actually really important to say, well, okay, what does this mean? It's also in a lot of ways inefficient to keep each set. So one thing that's interesting is that if you have a set of words, you can't very easily vectorize this, because if you have many, many words, many different words in a text, like a document, versus very few words in a document, you have to decide how big is my, like, essentially my set, how big is my feature? And that makes it actually really difficult to actually do things like calculations and stuff like this off of it. So like different sizes, different words. What if the word doesn't occur in one document, but it occurs in the other one? You know, you kind of have to make this like set, what's it called? Like set operations and stuff like this. So it just makes it a little extra like inefficiency. It's hard to compare. And then also, like you said, multiple words, right? If they appear multiple times, it's not distinguished whether multiple times make a difference, or that multiple, or the words occur multiple times in different texts. So it's nice to have those parts. So a better idea of this is just vectorization. So the reason why I will do vectorization in general is that we're basically going to try to take like natural language and try to convert it into, as best we can, into some mathematical representation. Why do we want to make a mathematical representation of our data? I mentioned this last time, so if you guys remember. Or any ideas? Why not just keep like the word like dog and stuff like this? Why do we need to make it into some math number? No ideas? So I'll basically just give you guys is that if we can get into a mathematical formalization, is that now we can actually use all of the tools that we've been using to do basically all the mathematical. Think of like when we did one-hot encoding. When you have the categories and stuff, you don't just keep it as like the different category names, right? Like blue, orange, yellow. You one-hot encode them into a vector, right? That way we can actually do like mathematical process on it, which means like machine learning algorithms, which includes things up to like random forests, support vector machines, all the way up to like neural networks and deep learning. Okay, so the way you can vectorize bag of words is, instead of saying things to say, oh, the set of tokens, we can instead say we can create a single vector to represent the document. So the document is going to be represented by a vector, and this means that this vector, every document will have the same size, which means it makes it easier to do math on top of it, right? And one way we can do this is basically a document term matrix. And so if you look in the curriculum, for example, what this looks like, basically the rows are the documents itself, and the columns are the tokens, right? And then inside those, inside like each of those value are these, in each of those rows are the different values of what happens. So what this kind of looks like, can I draw? Good. I was worried I was going to be able to draw. So what this kind of looks like is like, if I kind of do this out really quickly, is that each row is a document, right? So this is like, you know, let's say a corpus of tweets. I like using Twitter data, right? So like this is a tweet right here. And then basically in this columns is saying something like, okay, the word dog, because let's say we already tokenized it. Dog, this is cat, this is like jump. And then in those rows, we can say, oh, okay, dog occurs 1 time in this tweet, occurs 0 times with cat, occurs 1 time. Let's say this tweet has like dog mentioned like 3 different times. It doesn't mention, it mentions cat once, but not jump. And this one has, 0 jumps, but mentions about cats a bunch of times, nothing about dogs. So this is kind of like how we can represent, this document, right? It's like, okay, now we have a vector. And so this one vector on this row here, this row represents the document and it would be a vector, okay? Now we can also do the frequency. So we just divide it by how frequently these words actually occur. That's what the document term. So instead of having a whole number here, you would have some percent, right? And this is say, okay, like, if let's say dog is on here, it's the percentage of those words that are actually used in there, okay? And just kind of, I have a little like, how is this better? Well, now we can actually do math with it, right? So we can do things like we compare how frequently, how common they are. We can see saying, oh, like this one uses dog a lot more than like this one over here. You can compare how similar they are. So maybe, for example, I didn't have a good example here, but maybe, for example, if you use the word dog, you'll use the cat, jump as well. But if you use the word cat, you are very unlikely to use jump. So you can kind of make a comparison of like what those documents are like. And a really good way of doing this is cosine similarity. Do you guys, give me a thumbs up if you guys remember what cosine similarity means or what that does? Okay, I see a thumbs up. I probably saw a couple like head shakes, a couple people like not wanting to like it, like probably not knowing what to say about this. So just a really quick refresher is that cosine similarity, if you imagine this is like a graph, right? And here's like my first vector here, my second vector here, right? We can kind of represent vectors with like arrows, right? Cosine similarity basically just measures how far the angle between those 2 vectors. And what's really nice about this is that it doesn't have to be in 2D, it doesn't have to be in 3D, it can be in whatever dimensional space the vectors are in, and we can always measure that cosine similarity, basically saying how far of an angle this is. So this is why it's really useful, okay? And really, the reason why we don't use a dot product, I kind of mentioned this part right here. If you use a dot product, basically you wouldn't be able to say specifically, like if they're pointing in the same direction, other directions, stuff like that. It basically it takes off too much information, where cosine similarity keeps information about like how close together. Okay, does this all make sense? Okay, give me a thumbs up, sideways, thumbs down for this bag of words representation. Okay, so main thing I will say about bag of words is that essentially what you're doing is just saying how frequently are the words used, and you're just representing it with a vector of saying how frequently they are. So each document is still a vector of the same size, and the values in there just represent how frequently each word is being used. Okay, so you can see like relatively simple. Like if I asked you to kind of do this yourself, you could probably figure out a way relatively quickly how to, produce like something like that. Okay, so let me get my controller back. All right, the next one is tf-idf. I have heard people pronounce this. I can't even tell you like how people pronounce it, but I usually just say tf-idf, and that's where most people do it. But I have heard something like TFIDF or something like that, and I'm like, I didn't even know what they're talking about at first. But just know that maybe you might hear people pronounce it differently. So one disadvantage to bag of words is that every word is equally important, which kind of like, if you think about how this is done, right? We don't know what word is important. But we know, like, for example, there's like how we can remove stop words. We know certain words have more importance, have more meaning, have more context than other words, right? And this is where we can actually use tf-idf, which we'll see actually is an acronym to kind of help represent this information. So this is where we talk about document frequency for characterization, okay? So you can think of it as some set of documents have more frequent use of certain words. Kind of like I said, like, God with like in like the New Testament versus like Moby Dick, right? So the idea here is that we're going to take 2 different parts, the term frequency, which is what TF stands for, and the inverse document frequency. So the idea here is that the term frequency is how much over the overall, let's see here, like how frequently that term is used in the document over just how many terms there are. So like if you think of it like the term frequency of God in like the New Testament over Moby Dick, it's probably going to be a higher number, right? God is out of all the words is going to be used a lot more frequently, right? Than like God is used in like Moby Dick. Okay, IDF, which is the inverse document frequency. Typically, there's different ways you can do this, but typically what we do the log value of just the total number of documents divided by the number of documents with terms, with that term. So the idea here is that you say, okay, how many documents actually use this term, let's say the God. So if you have like different, documents, and documents could be like tweets, right? Like they don't have to be super long, like I'm talking about text, but like, or you can even be sentences within, like a book. So the idea there is like how many, documents actually use that term, okay? And we basically take that value and we put them together and we get this one value, which is the TF-IDF. And that represents essentially the importance of words, which hopefully that makes sense. If the word is being used more frequently, it's probably more important. Also, if it is a word that's not commonly used in other text, or other documents, that probably makes it a very distinguishable word, right? So like, for example, if you use the word, I keep using like documents like text, but you should think of it like a book. But like if you imagine like Harry Potter and using the word muggle, right? Muggle is not a very common word at all, like in other books, because it's a made-up word, right? So it's a very distinguishable characteristic, right, of that book. So this is kind of like what it's trying to measure. It's like, okay, how frequently is this term being used, and how rare is it amongst all the other texts that we're looking at in the corpus? Cool. Does that make sense to everyone? And that's the intuitive idea of this TF-IDF. All right. So again, we can basically make, you can think of this, again, another like way we can represent numerically our values. Okay. And then our last one is the most exciting one, I think, is the word embedding. So I actually have a whole notebook on this because we kind of talked a little bit, I think we might have talked about it in another study at one point about embeddings in general, but we'll go into more details specifically about word embeddings. So before I move on though, any questions about bag of words or TF-IDF? Go, Giovanna.
Sorry. I'm just curious, when you're doing these calculations, I have two questions. One is the number of documents with the term. It doesn't matter how many times the term appears on different documents. If it's mentioned once, you count and it doesn't matter, right?
That's right, yeah. That's where this part right here, the inverse document frequency, just saying, does it occur or not?
Okay. And the second question is, when we do that in a real life project, how do we treat words that are very common and may not have that much meaning for the overall document, like and, pronouns, that kind of word? Is there a way to filter them out, or is it not wise to filter them out?
Yeah, and that's actually what we might have talked about. You might have not remembered, or maybe you weren't here yet last time. We talked about filtering out words. Those are usually, we talk about stop words, basically words that don't really like have any real meaning. So here we go. I'll show you a little bit. So like, for example, I, me, my, myself, than, oh, like the words that like a, and, like those things that don't really have extra meaning. And this will depend on the corpus as well, right? And also languages, right? If you're looking at Spanish versus, English, you're going to have different stop words. But you also have them in different contexts too. Like maybe certain corpuses, I think it's corpuses, not corpi, but different corpuses will have different words that don't really have that much meaning to it. So I think I gave an example like the Smurfs. Like if you said like Smurf this, Smurf that, like all these different things, it's not really an important word that doesn't give much meaning. That would probably be part of your stop word. Okay. Cool. Make sense, Giovanna? All right, cool. So moving on then from our, TF-IDF and bag of words, talk about embeddings.